Okay, welcome back to the C++ course. This is Chapter 11. You can see the topics here, more about classes and object-oriented programming. So we got a gentle, hopefully gentle, introduction to object-oriented programming a couple lessons ago. We're going to take that and extend it and build on it in Chapter 11. So here's our definitive list of topics. The this pointer, this is always awkward to teach about and lecture on because it's the word this. This is a C++ keyword, and yeah, we're going to learn about it. Pointer and constant member functions, static members, friends of classes. This is something actually that's pretty unique to C++, this idea of a friend of a class. We'll check out what that means. We're going to look at member-wise assignment, copy constructors, operator overloading. This stuff is pretty cool. Overloading operators in your own custom classes. We'll take a look at the R-value references, move operations. Then we're going to check out type conversion operators, convert constructors, aggregation, and composition, some good high-level object-oriented programming techniques. We'll check out inheritance, very important concept. Take a look at protected members and class access, constructors, destructors, and inheritance, and overriding base class functions. Lots of stuff to get to. Let's get into it. Starting off, the this pointer and constant member functions. So this, as I mentioned, is a keyword in C++, and most object-oriented programming languages have some kind of concept or notion similar to the this pointer. And it's an implicit parameter passed to every member function. So anywhere you're defining your own member functions in your own custom classes, you have access to this very special this keyword, this pointer. And it points to the object calling the function. Now some languages call this self, or I think some languages call it like me even, or my, but you could think of it as this or self. I think self is actually a better way to think about it. Other languages, like I say, use self, and it's just a more straightforward, intuitive way to think about it, because if you use this, you're saying my own class, myself, this, me. So we'll take a look at this and how to use it. Then the const member function, and that is saying that it's basically a promise you're making to other programmers that are using your classes. It's a promise to not modify the object that's calling this particular member function or method. Here's a quick example of this, and the easiest and probably earliest, most straightforward way to see why this may be useful is in the context of your setters. In your own custom class, we talked about getters and setters are where this keyword becomes particularly useful. You can use it to access members that may be hidden by parameters with the same name. So if you remember with our setters here, so we have a private int called num, then we have a setter for num that's public, returns nothing. It accepts an int called num. Now this is a way, using the this keyword is a way to, I'll use a big word, disambiguate which num you're referring to in the body of the setter. This is nice because programmers tend to not be super duper creative with their variable names. And in the past, we've had to come up with like a different name in the setter inputs so that we would know the difference between the parameter and then the private member or the private property of the class. So using this, when we say this arrow num, we're referring to the private int num defined in the class. If we just say regular num, we know that that just means whatever is passed into the setter. Let's take a look at a hands-on on page 719. Let's just get our hands dirty here a little bit. Let's get warmed up with this fairly straightforward, simple example of the this keyword. Create a new project. Oops. EX11-1, solution name, Chapter 11. Get myself organized here. Okay. So if we have a class called example, very creative, we have an int x, which we know we didn't specify, so we're going to assume that it's private. Then we're going to say we have a public section. By the way, I would say this is not very good technique. I would always want to see my data members and my member functions declared in a private or public or protected section. Nevertheless, in our public section, we're going to have a constructor called example that accepts an int called a, and we're going to inline the definition of this constructor and just say x equals a. We're going to have a void set value passing in an int. Oops, I need my semi there, not there. And then a void print address and value. Now in our example code here, it looks like they're defining the header file separately from the implementation. For us, I think we'll just do that all in one kind of compact location here. So we'll go ahead and define set value and print address and value. So to do that, we say example : should we start with the constructor? No, we already defined that. Let's do set value, passing in an int called a. We're going to say x equals a. This happens to be a void method. Then print void example : print address and value. Now in this, we're just going to see out some stuff. So see out, and to do that, we need the standard namespace, see out the object at address. This, check that out, this keyword has value. Now check this out. We're going to dereference this. So remember, in the slides we said that this is actually a pointer. It's a memory address. So if we want to actually get the thing that this is pointing to, in other words, ourself, we're going to dereference this, just like we've always done, and then say .x. That will get us at the private x property, and then an endl. Cool. Also, I would point out here, I don't know why they didn't do this in this example, since we're talking about this keyword. We've got int a, and then we're saying that x equals a. Well, we're already talking about this, so why don't we do, let's pass in an x here. Instead of saying x equals a, we'll say x equals x, but we need to specify which x we're talking about. In this case, we're going to say this arrow x equals x. So this is a way of saying this guy means this guy, and this x means whatever is passed in here. Now we'll just use our custom class. So we'll create example obj1 passing into 10, comma obj2 passing in a 20. And we'll see out addresses of the two objects. Let's see, the address of obj1 and address of obj2. Okay, so that's going to show us show us using the ampersand operator to get the address of the obj1 object. Then we're going to check out obj1.print address and value, obj2.print address and value. Let's see what we get. Hopefully you can guess. Indeed. So the address of the two objects, I'm not going to read that, but you can see that. Basically, the address ends in hexadecimal FBC4 and FBE4. As we would expect, hopefully again you guessed this, but these two addresses match. We're getting at the same memory address in sort of two different ways. We're getting at it outside of the class implementation here in int main. We're getting the address in this way. But once we're actually in the class and we're calling print address and value, we're getting at the address of the object sort of internally by simply calling this. Remember, this is a pointer. If we see out this, we're going to get a memory address, and that's exactly what we see here. And then you can see the values that we get when we dereference this, pointer.x. And remember too, again, it's confusing. This way of accessing this is asterisk this, surrounded in parens, dot x. The shorthand for that, if you remember back a couple chapters ago, is simply using the arrow notation. Hopefully this is more comfortable than this convoluted mess. Try to stick with arrow notation whenever possible. And it should be possible most of the time. Okay, that's the this keyword. Constant member functions declared with the keyword const. We have encountered const elsewhere. But when const appears in the parameter list, such as this one, where you have a setNum method returning an int accepting an integer constant called num, the function is prevented from modifying the parameter. Basically, it's read-only. So not only is this kind of a visual cue to the programmer that, hey, in setNum, we are not going to be modifying num in any way. It's not only a visual reference, it is actually a compiler-enforced rule. When we use const, we're not allowed to modify that. It is read-only. The other way to use const is as follows. So when const follows the parameter list like this, the function is prevented from modifying the object that's calling it, I would add here. Some more key terms here. Static members. So static member variable, there's only one instance of the variable for the entire class. It is shared by all objects of that class. This again is a topic that transcends programming language. It exists outside of C++. Most object-oriented languages have this notion of static member variables and static member functions. And what they are, again, is it's a data member inside of the class that's shared across all instances of that class. And in fact, you don't even need to create an instance of the class to access a static member variable. Static member function, same idea, can be used to access static member variables and can be called before any class objects are created. So we don't need to say object1 dot member function. We can just say class name dot member function. Here's a concrete example. So when we use these things, we must use the static keyword like so. So we have a class called intVal. In our public section, we have a constructor. That's not actually correct. We need to capitalize that I. To do our constructing, as you can see here, I'll draw your attention down here to the private section before we talk about the rest of it, because notice here we have a static int val count. And val count, you can see here, is incremented in our constructor. And this is a classic way. This is usually how people teach static data members. They usually say, hey, here's a way that a class can keep track of how many instances of that class have been created across the program. So val count, when I create a new instance of int val count is ++, so it's going to be, I guess, 1. When I create another instance of int val, then val count is going to be 2. So it's sort of like a way to remember data across instances of your classes. Must be defined, outside of the class. So like here we have class int val in class declaration, looks like this. And you can also define it. Oh, I'm sorry, you can access it, I would say. Few typos in this lesson's PowerPoint. Definition outside of class. You can also get at it in this way. Because the static int val count is static, you can access it like this. Only you can't in this example because it's, as we saw, private. but that's how you would do it. So like I say, you can access or modify these by any object of the class. Modifications by one object are visible to all other objects in the class. I think that's a perfect way to define this and summarizes the idea quite nicely. So here we have two instances of that class name, int val. Right here, val1 and val2. They both can access the shared val count data member. Let's take a look at a hands-on and see if we can use statics. New project, console app, ex11-2. Just as a little refresher here, since it's been a while since we've used object-oriented programming techniques, let's try to actually construct this. We'll create this in kind of the proper way, where we have the header file separate from the, looks like separate from the implementation. So I'll go ahead and activate this project first of all, set a startup. I will add a class. Class name looks like is budget. So we get the budget.h and we get the budget.cpp. Here's the h and here's the cpp. Cool, so we'll start with the header file. And this pragma once thing, if you remember back when we talked about OOP initially, I kind of said like, just kind of do this. This if and def define end if thing. I think this pragma once kind of takes care of that for us. And I'm going to trust Visual Studio knows what it's doing on this and just kind of be happy with the pragma once directive. But anyway, so we have class budget, private section, static, double corp budget, and double division budget. Public section, constructor, takes div budget, sets it equal to 0. Void add budget, accepts a double called b, and takes div budget plus equals b. So div budget equals div budget plus b, whatever is passed in for b, and then corp budget plus equals div budget. So the looks like the corp budget, just kind of thinking about this intuitively, kind of keeps track of all divisions. That's why the corp budget is static. So we're going to have a bunch of budget objects created. Presumably those are going to be like representative of the divisions, but each division kind of knows what the overall corporate budget is because again, this is a static double. Good, so that's add budget, and it looks like we're doing our implementation here in the header file as well, so no problem. Double get div budget is a const that returns return div budget. Double get corp budget const return corp budget. And I think that's our implementation. I don't even think we need the .cpp file. Let's head back over to the main CPP file. Go ahead and include my beloved iomanip. Let's include budget.h. Ours is capitalized. Theirs is not in the textbook. No problem. We'll use namespace std. Okay, notice here outside of main, we're going to say double budget colon corp budget equals 0. So we're initializing, we're defining the static member of the budget class. Notice I have not created any instances of budget, but I can still access that corp budget static property. That's what static is. Inside of main, we'll have a const int n divisions equals some number 4. Then we're going to have, this is good review too, an array of budgets of size n divisions. This is an array of budget objects. We'll have for int count equals 0. Count is less than n divisions. Count plus plus. And here we'll create a local variable called bud. Cout, enter the budget for this div. A little shorthand notation, never heard anything. Cout, and we're going to print a prompt here that's going to be count plus, count plus 1. So we're going to make the count variable basically a little more user-friendly, so a user wouldn't see enter the budget for this division 0. Users would rather see division 1 if they're entering data for the first division. All right, then we'll cin bud, and then we'll say divisions, that array, at location count dot add budget. We're going to pass in bud, and that's going to get that set for us. Cool, so we've got all our data populated here from our for loop. Cout, set precision. I don't know why I loathe these iomanip functions in library so much. Cout, they're just awkward to use. Show point, and then fixed. New line, here are the divs. Div budget requests for int count equals 0. Count is less than n divisions. Count plus plus. Body of the for loop, cout. Division count plus 1. Then we have, what is this mess? We have a escape sequence, basically /t for a tab, and then a $, then a space, then a double quotes, then a semicolon, then a cout. We're going to print the actual data now. Divisions at location count dot get div budget. Don't forget your parens, end line. Then finally down here, we'll cout total budget requests /t $. Sounds like a rapper. $. Cout divisions at location 0 dot get corp budget. And that might seem a little weird. Let me explain that. And then return 0. Let's run this first to make sure everything's good. We've got to input data for 4 divisions. And I'm going to make this easy. I'm going to say 10, 11, 12, 13, and assume that math works. I think it probably does. Total budget request, $46, and there's all my individual budgets. So why do we say divisions 0 dot get corp budget? Well, if you remember, get corp budget is just a method, a public method on our budget object. And within that get corp budget, all it's doing is returning this static corp budget double. So it is a little dangerous. It's assuming that we have divisions. Like in another language, you might get a warning here saying, hey, we don't know if you actually have divisions to do this. But in this case, it's okay. We've basically guaranteed they're going to be there. We could say divisions 1 dot get corp budget, or 2 or 3, not 4, because we don't have an index 4. We have a max index of 3 in this array. Size is 4, but max index is 3. So we could call get corp budget on any of those and we'd be fine. Cool. Grab a drink here and we'll continue. So static member functions. So declared with static before the return type, they look like this. Static int get val count, return val count. And we also have the static int val count private data member. So we've got the function here, the method, and we have the static data member. It can be called independently of any class objects through the class name. So this is how you would actually call that thing. You could just say class name : get val count, where val count, remember, is static. Because of number 2, the this pointer cannot be used. So we can't use it because we don't have any instances of the int val class. You can call this before any objects of the class have been created and used mostly to manipulate the static member variables of the class. Let's do this example as more of a hands-on or a read-only hands-on. It's just going to show us an example of a static member function. And let's just glance through this. Let's see, we've got our constructor. Here's our static double get corp budget and static void main office. So let's look for where those are called. Here's the implementation file. In here, this implementation looks a little different. So definition of the static member of budget class. So here, corp budget is this static data member that we're initializing to 0 when a new instance is created. Sorry, when the code is run, that's set to 0. Then we've got an implementation of the main office, which, remember, main office is a static method, so it can be called anywhere. What I really want to get to is the main method, where we can see that being used if we wade through this a little bit. Right here. That's the key. Class name is budget : main office allows me to call the main office static method with no instance of budget having been created. That's the key. And they're doing the set precision stuff. And yep, again down here, here's the class name, : scope resolution operator, get corp budget. We can use that static method without referring to an instance of budget. Next topic, friends of classes. So what is a friend function? And again, friend functions are pretty specific to C++. You don't see them, at least in this way, in other languages. It's a function that is not a member of a class, but it has access to private members of the class. A friend function can be a standalone function or a member function of another class. It's declared a friend of a class with the friend keyword in the function's prototype. And it may look like this. So a friend function may be a standalone function like this. So if we have a class called a class, inside of the a class definition, in this case just the header file, here's our friend keyword, friend void fset. So fset is the name of the function, where you are accepting 2 parameters, a reference to a class, reference to an a class object, and just a regular old int. Then notice when fset is defined, when it's implemented, we are not inside of the class anymore. There's no reference to the class a class when we're defining what fset is. The fact that it's a friend means, hey, we kind of trust you. We trust you, fset, to be able to work with all of my private data members in a safe way, in a responsible way. It's kind of ensuring a bond of trust between your class, its private data members, and whatever the friend function is you're kind of establishing that connection with. Maybe a member of another class. So here we have a class called a class. Here's a class called other class. In a class, we've got a friend void other class : fset blah blah blah. Key parts being here, in order to specify this as a friend, we refer to the other class name, other class : name of the friend function. Then down here in other class, notice again how we don't have any reference to a class. The friend connection, or the friend relationship, if you want to think of it that way, is established only in one of the classes. A class is saying, I want other class fset to have access to all of my stuff inside of my definition. Another example, an entire class can be declared a friend of a class. So here we have, so this is going to be a different use of the class keyword. So usually we see class when we are defining our own classes, like up here, class budget. But here we're saying, here's a class called a class. Then I have a friend class called FR class that can basically do whatever with me as it wants. A class, FR class can have access to all my stuff. Private, public, whatever. These two classes are now friends. Again, in FR class, there's no reference to, yes there is. There is a reference to a class here. I'll make sure I said that right back here. Yeah, I misspoke back here on the previous slide. Other class does have a reference to a class. When we say .x, right down here where it says c.x, if these two classes were not friends, we wouldn't be able to say c.x because, as you know, x is private. So they do kind of have references to each other, but the connection that friends establish is only done in one of the classes. It's set up so that other class can use a class's stuff freely. We'll do this 11.4 as a read-only. Feel free, of course, to type it out on your own if you like the extra practice. Try to keep these lessons somewhat manageable, digestible in a single setting. 11-4. I don't actually see. Yeah, here's the friend. Weeding through the code here to find the important pieces. Here we have a class called aux. Here we have a class called budget. In budget, we're saying here is the class aux, : add budget. That is a friend method to budget. So then up here in add budget, we can access budget's public and private data. Let's move on to the next page here. Static, looking for the friend keyword. That may be about it. All right. Member-wise assignment can use the equal sign to assign one object to another or to initialize a new object with an object's data. So here we have the class is called capital V, so some random class that was defined called capital V. Capital V, V1, comma V2. You can do a bunch of stuff here, statements that assign values of the members of V1. Once you do that, then you can say V2 equals V1, and then create a new V called V3 and assign it equal to V2. (11-5). Okay, class called rectangle. We've got some private data here. Double width and length. We're doing the things that you would expect in a rectangle class. We're getting the width, getting the length, printing those out in a convenient output constant method. Then we have int main here. We've got a couple instances of the rectangle. Box1, box2 with some data. Display the rectangle's objects. Before the assignment, box1's data is box1.output. Box2 is box2.output. Then we're doing the reassignment and then displaying it. And to see kind of what we're getting at here, we better take a look at the output. So before the assignment, box1 data, width is 10, length is 20, box2, 5 and 10. After we do that assignment, after we say box2 equals box1, then they are the same. So when we say box2 equals box1, we copied the width and length variables of box1 directly into the width and length variables of box2. Again, this is called member-wise assignment. Occurs when one object is initialized with another object's values. Difference between assignment and initialization. Assignment occurs between two objects that already exist. An initialization happens to an object when it's being created. You're initializing it. Okay, copy constructors. So a copy constructor is a special constructor used when a newly created object is initialized with the data of another object of the same class. The default copy constructor copies field to field using member-wise assignment, and it works fine in most cases by default. Problems can occur when objects contain pointers to dynamic storage. So when your classes get a little bit more complex like this, where you're dynamically creating and destroying memory, you can have some issues. Let's take a look at a hands-on. Okay, we've got a simple class called address. We've got a string street. We've got a constructor, two constructors, I guess. One of the constructors is calling set street. The other one is simply setting street to a blank string. And we have a constant getter here. Mary and Joan live at the same address. So says our comment. Address Mary. You can see what that looks like. Address Joan equals Mary. So they're going to be at the same address here, and you can see that in the program output here. They live at 123 Main Street. Now Joan moves out, so we're going to say Joan.setStreet that. Now Mary lives at Mary.getStreet and Joan.getStreet. You can see they're different now. So the default constructor causes sharing of storage. So here we have a class called CPClass and an instance of it called C1 passing in 5. Some if statement true, which is always going to run. Now we have CPClass C2 equals C1. Now C1 is corrupted when C2 goes out of scope and its destructor executes. So destructor of one object deletes memory still in use by the other. That can be a potential problem. And modification of memory by one object affects the other if it's sharing the same memory. That's kind of illustrated by this point. So what if these are in different scopes? And say C2 goes out of scope and its constructor basically destroys the instance, destroys the data. Now what is C1 to do? I don't know. That's up to us to figure out as programmers in our specific instance. So programmer-defined copy constructors takes a reference parameter to another object of the same class, uses the data in the object passed as a parameter to initialize the object, and the reference parameter should be const to avoid potential for data corruption. Copy constructor avoids problems caused by memory sharing because we're kind of doing it, we're kind of handling those details ourselves in the definition of the copy constructor. It can allocate separate memory to hold new objects' dynamic member data if it needs to. It can make the new object's pointer point to the new object's own dynamic memory and copies the data, not the pointer, from the original object to the new object. So again, this is more of like a manual way, and what you're trying to do is, just like this point says, copy the data, not the pointers. Here's an example. Copy constructor, so CP class. Here we have a pointer to an int called p, and we have a public CP class constructor that accepts a reference to another CP class called object. Then we're taking p, dynamically creating a new int, and then we're saying dereference p, set it equal to, wrap your mind around this syntax, take some time to digest this, pause it, rewind it if you need to. Dereference the private p and assign it the value of dereferenced obj's address dot p. Yes, we are copying values. So this class is accepting a reference to a CP class or an address. We're going to dereference our p and assign it dereferenced obj that was passed in dot p, so that other things p. Okay, CP class int v equals 0, so p equals new int. This is just another basically version of the constructor. We're going to say p equals new int, and then we're going to dereference p and assign to it whatever is passed in as v. So the two constructors here, one that accepts a reference to another class of the same type, and one that just accepts a regular old int. And the programmer can decide which one is suitable for them and their needs. The destructor, if you remember, this tilde represents destructor, freeing up the memory that was allocated by this class, simply deletes the pointer p. So when is this thing used? It is called when an object is initialized from an object of the same class, an object is passed by value to a function, an object is returned using a return statement. So remember, by value basically creates copies of the thing that you pass into the function if it is by value. It is not a pointer to the thing, it is a copy of the thing. So when we say copy, yep, copy constructor. When we return an object from a function using a return statement, that's also a copy constructor. Initialized from an object of the same class as well, copy constructor. Okay, the minutia of object-oriented programming in C++. So object overloading, I like this topic. I think it's pretty cool. So we already know what these two terms mean. Take some time to think about it, see if you can figure out what this idea is. We'll start with overloading. We talked about overloading in the functions chapter, where we said here's two functions with the same name, but their signature differs. So maybe we have a void func1 accepts no input, then we have a void func2 which accepts maybe an integer. Whatever it does with that data, that's fine. We overloaded the function. We're using the same function name more than once in a different way. Now what's operator? An operator, remember, something like equal sign, plus, minus, multiply, divide. Lots of operators in C++. The cout, angle bracket, that's an operator. We can overload those operators. So we can say things like, if I have a class called player that I've defined, if I overload an operator in the player class, I can define what it means to say player1 plus player2. What does that mean? By default, C++ doesn't know. But if we overload the plus operator, we can tell C++ exactly what it means to add two players together. Maybe it doesn't mean anything. Maybe that's a bad example and you don't want to add players. Fine, you don't overload the operator. But if you wanted to, you could. The name of the operator, and full disclaimer, the syntax for this, to set this up, is nasty. So the name of the function for the overloaded operator is this keyword, the keyword operator, followed by the operator. So if you wanted to overload the plus sign, this is what it looks like. Keyword operator, the operator you want to overload, which is plus. Operator equals means you want to overload the equals operator. So operators can be overloaded as instances, instance member functions, or as friend functions. So you actually define these things just like you would any member function in your class, only the signature is what's quite different. The overloaded operator must have the same number of parameters as the standard version. So for example, operator equals must have two parameters since the standard equal sign operator takes two parameters, one on the left, one on the right. You could also overload plus plus, minus minus, plus equals. A binary operator that is overloaded as an instance member needs only one parameter, which represents the operand on the right. Down here is our first example of seeing this in action. So here's what they're doing. They're defining what it means to add two op classes together. The left operand are the overloaded binary operators. The calling object, the implicit left parameter is accessed through the this pointer. So let's digest that a little bit. So think about what it means when we use the plus operator, the addition operator in C++. We say var num equals, I don't know, a plus b. You've got two operands, that's the word I'm looking for, two operands. One operand is on the left of the plus, one operand is on the right. So when we say we're going to overload the plus operator, we need a way of getting at both of those pieces of data. We need to get at the calling operand and the other operand. And it looks kind of like this. So when we say operator plus op class R, so we're passing, it's sort of weird to think about. You have to think about overloading operators as like creating functions. So let's just go into the implementation. Op class sum. So we're creating a local op class type called sum. We're saying sum.x equals this arrow x. So the x that's in this class that's defining the overloaded operator plus whatever this x is. And then return that sum. Yeah. So remember what we're returning from this, because we're saying basically op class plus op class, we need to return an op class in this example. Maybe we don't. You could have it return whatever you want. You could have it return whatever you want. In this case, we're returning a sum that is of type op class. So just remember, we're returning this instances x plus whatever the x of the thing passed in is. To invoke it, no real surprises here. An overloaded operator can be invoked as a member function like this, or you really wouldn't see this too much. I would personally just ignore this method of calling overloaded operators. Just use it like you would a normal addition. Can be evoked as more of a conventional manner. So op class A, B, and S, we can say S equals A plus B, where A is an op class, B is an op class, and the plus does this. Okay. Yeah, it's a little confusing. It's a little confusing to explain too. So overloading the assignment operator solves problems with object assignment when an object contains a pointer to dynamic memory. So the assignment operator is most naturally overloaded as an instance member function and needs to return a value of the assigned object to allow cascaded assignments like this. So assignment overloading as a member function. Let's see, where is it? There it is, highlighted in blue here. So we have keyword operator. The equal sign is what we're overloading. We're returning a CP class, and we're also accepting a CP class. And I'm hoping we'll see the, yes, implementation here. So this is that overloaded equal sign. Again, returning a CP class, accepting a CP class called R. All we're doing here, we do have that private pointer to an int called P. So we're dereferencing that private pointer, assigning it equal to whatever this CP class is, dereferenced .p, that private P of the thing that we're passing in, and then returning a pointer to the thing that called the overloaded operator. Take a look at an example here. I'm going to delete this horrible syntax. Goodbye. Here we have CP class A, which is not initialized to any data, and then X, which is passing in 45. If we pass in a value 45, then we actually are assigning something to the pointer P, the dereferenced pointer P. And we can just say A equals X. And when we do this, this is what runs. Hopefully it's a very straightforward idea that unfortunately C++ mucks up in its syntax. I really, really like the idea. I hate the syntax. So some notes. So overloading can change the entire meaning of an operator. Most can be overloaded. You can't change the number of operands. You can think of this as like the plus sign is deeply, deeply defined in the C++ language. We can't fundamentally change how it works, but we can like extend its functionality and build on top of it. You cannot overload these operators. Where does it go? Like we said, overloaded operators can be a member function of the class. That's what we've sort of just seen. You can use it to access private members and use of the this pointer. You can also make them separate functions outside of the class, but if you do that, they have to be friends of each other. Overloading types, so ++, increment, -, decrement, they're overloaded differently for postfix versus prefix. So if you remember the difference between the two, I'll just pull up a random piece of code here. Int x equals 1. So prefix is ++x. Postfix is x++. You guys are probably more comfortable with x++, if I would guess. We use that in like for loops a lot. But they are overloaded slightly differently. Overloading relational operators should return a bool. So you can overload relational operators. Like equals is something equal to another. That's kind of nice. Because if you have two player objects, you can define what it means for two players to be equal to each other in like a game dev scenario. And it should return a bool if those two objects are equal to each other or not. So you can overload a stream operator. So cin in this case, cout in this case. They must return an iStream or an oStream, so input stream or output stream object, and take iStream or oStream as parameters. Best overloaded as standalone operator functions. You can also do this, which is kind of cool. The brackets that we typically use in array syntax, you can also overload those. You can use these to create classes that kind of act like arrays. You can provide bounds checking on subscripts, for example, because as we know, we don't really get that. When you overload square brackets, you return a reference to the object, not the object itself, to return a reference or an address. A lot of talking here. Let's see what we have for hands-on examples. Let's get our hands dirty with this guy. 11.9. Next. And this looks like overload.h. So we will add, add a class. We'll call it number array. It's going to create both files. I wonder if we can turn this off. Can I just delete this? We'll see what happens. Testing on the fly here. We just need the header file, I think, because let me double check that. Nope, we need the implementation too. All right, give me the implementation. Some of the implementation is done in the header file. And that's okay. And I'm looking for my header. Here it is. It's a lovely blue. Wait a minute. Oh, I see. What I was confused about is the name of the files is different than the name of the class. I don't like that. For reasons that you just witnessed, it creates a little bit of confusion. Like the class name is number array, but the file name is overload.h. Much prefer keep your class file names the same as the class name itself for reasons that you just saw. Okay. Here's my header. Good, private, a nice blue hue on my code now. Double pointer, a ptr, int array size. So here's our public section, our public constructor. No, sorry, we're overloading the equal sign. If you remember, we're going to return an address of a number array. Here's the keyword operator, followed by the operator we're overloading. Okay, as parameters, as input, we need a const reference to another number array called right. So I like that they called it that actually. This really drives home that when we say one number array equals another, the number array on the right side of the equal sign is this thing, is right. Okay, some constructors. Number array. So we're going to allow the programmer to initialize a number array object by passing in a reference to a number array object. Kind of neat. We'll also do one where they can just pass in an int called size and a double called value. We'll deal with our destructor. There we go. Keyboard shortcuts. I have a very tiny keyboard, so I have to do finger gymnastics to type a tilde. So here we're going to do a little bit of logic in our destructor and just say if array size is greater than 0, use the delete for arrays APTR. Just a little check here. Just if there's something in the array, if the array size is greater than 0, delete it. Otherwise, don't waste your time deleting it because there's nothing in it anyway. Void print is a const, and then void set value. Cool. Over to the implementation. So we've already included the number array header. Let's include IOStream. Like so, okay. So here's the overloaded assignment. So number array, we're returning a reference to a number array. So here's the class name, number array, : operator equals, passing in. Again, think of this overloading as like passing in parameters to a function, because that's what the operators are. They are functions. We don't use them like functions when we're just writing code in our daily lives, but that's what they are behind the scenes. So we have to define them like they are functions. So the assignment operator is going to take a number array on the left and a reference to a number array on the right. See if I can resize this just a little bit. Yeah, squeeze it all on one screen here. Okay, here's the logic for our assignment operator with number array 1 equals number array 2. If this, remember this is a pointer, if this is not equal to the address of right. So what we're doing here is comparing two addresses. Remember, we're saying number array 1 equals number array 2. If the one on the left, that's what this means, is not equal to the one on the right, and when I say the one, I mean the address. If the address of the left is different than the address on the right, then go ahead and do all this stuff. Do a check. If array size is greater than 0, deal with it. Delete that pointer. Yeah. Then we're going to set array size equal to rights.array size. Okay, remember, we're dealing with an equals operator. So we are going to take this thing's APTR, delete it, and then basically reassign it to whatever the right operand is. APTR equals new double array size. So we have to use new here because we're dynamically creating an array of size array size. We have to use new. array size could be different. We'll say for int I equals 0, I is less than array size, I plus plus. Then we're just going through and moving over, copying over, I should say, very different. Copying data from one number array to the other. APTR at location I equals write.aptr at location I. Really chew on this. Make sure you can understand what is going on here with this overloading of the equal sign. Pause, rewind, do whatever you need to make sure you can digest this. Then we're going to return dereferenced this, which is going to fulfill this requirement. Okay. Basically, we want to say number array 1 equals number array 2, clear out the stuff in number array 1, reassign it, copy over the stuff from number array 2 into number array 1. Cool. That's the assignment operator overload. Here's our copy constructor. Number array const number array. So yeah, that's happy. Okay, array size equals obj.array size. APTR equals a new array of size array size, type double, then loop and fill that thing up with data. APTR at location I equals obj.aptr at location I. We've got a constructor. Int size 1 double value. I want to point something out here in case the copy constructor idea wasn't clear. Copy constructor, it is still a constructor. Like, this is constructor syntax. There's nothing special from a C++ keyword or anything like that perspective. It is just a constructor. It is just a special implementation of the constructor. When we say copy constructor, all we're doing is passing in another object of the same type, reference. Passing in a reference to another object of the same type, and then simply copying all that data of the other object into a new instance of our number array object. It's like a way of quickly filling a new number array with data from another number array. Then we have this sort of traditional number array constructor where we're just passing in some data that's going to fulfill the private data members. So array size equals size 1, APTR equals new double array size, set the value, passing in value. Okay, here's a function, or method I should say, number array, returns nothing, set value, accepts a double value, for int I equals 0, I is less than array size, I plus plus, APTR at location I equals value. So it's like you pass in one value and it's copying that value to every single slot in that array. There's a little print method, void number array : print, and it is a const. Good. For int I equals 0, I is less than array size, I plus plus, and just see out whatever is in APTR index followed by a space. Some deep review here. Remember, in our header file, we never actually declared an array. We created a pointer to a double, pointer to a double though, and an array size. So we never actually like used square bracket notation and created a new array. We're sort of using the sneaky implicit way of doing that. If you want to think of it that way. We are using new double here to do that, but we didn't actually do that in the header file. Okay, so now we have our main file. And we need to iomanip include and then include number array.h. Remember, when we include our own classes, we enclose them with double quotes and must include the .h. Let's use now what we've just created. Number array first, passing in a 3 and a 10.5. Number second, passing in a 5 and a 20.5. First object's data is first dot print cout endl second object's data is second dot print. Call the overloaded operator. Okay, cout call overloaded equal. We'll do an endl. First equals second. Now display the value of the two objects, so we can just say first.print. If I can type, and then second.print. I think we need an endl. Excellent. Notice how it takes a little longer to compile and link all that stuff together. But let's make sure our output matches theirs. Sort of, I guess. So we've got basically two different data sets here for the first, 10.5, 10.5, 10.5. Same thing here, 20.5, but what, 5 times? When we call the overloaded equal sign, now notice how they're both the same. So we, not only did we copy all the data from one to another, we also changed the size of the array from one to the other. Cool. That was a long one. Let's take a read-only view of page 754. I don't know why we have this lovely blue hue on our textbook now. Demonstrates the length classes overloads. So this guy overloads plus minus double equal sign for comparison and less than for comparison. So we have some class called length.h that was defined somewhere. We have 3 instances of length objects here. We have 2 ints, enter a distance in feet and inches, good, set it, enter another, good, set it, set length, test the plus and minus operators. So we're going to say take our third length object, set it equal to whatever first plus second is. Then we can say third.getFeet, third.getInches, and we would see that in the implementation of length.h, we would basically just be adding up the feet and the inches. You can also test to see if 2 length objects are equal to each other by overloading the double equal sign in whatever the implementation of this is. Oh, here's the implementation. Good. Let's just take a peek. And they've done it via the friend keyword. So let's just pick one. Let's do like double equal sign. So friend bool operator, double equal sign. Remember, treating this as a function, we need two length objects to compare for equality. So we have length A, length B. Also, we're overloading the input and output stream operators. That's handy. What that'll allow us to do is just cout bracket bracket a length object, and it'll print whatever we've done for overloading that, like here. So when we say cout angle bracket some length object, we're going to print out a.get feet, feet, a.get inches, inches, and then return out. That return out, remember, is just some special syntax we need when we overload the angle brackets. And I would strongly advise you to look through this entire implementation of the length class. This is a really good demonstration, full demonstration of overloading these operators. A very practical one too. Yep, they go through them all. Cool. Cool. So move assignment and the move constructor. So a fairly new feature, relatively speaking. So copy assignments and copy constructors are used when objects contain dynamic memory. Deallocating memory in the target object, then allocating memory for the copy, then destroying the temp is resource intensive. This is just saying that all that manual work that we were doing takes time and effort and computing time too. So moving assignment and move constructors, which use R value references, are much more efficient. So the move assignment, when we're overloading the equal sign operator, and move constructor, use an R value reference for the parameter. The dynamic memory locations can be taken from the parameter and assigned to the members in the object invoking it. You set dynamic fields in the parameter to this special null PTR or null pointer before the function ends and the parameter's destructor executes. This is not terribly new, I guess. It was introduced in C++ 11. What this is saying is this idea was basically already done internally inside of the compiler. Even though we couldn't explicitly do it as programmers, the compiler is doing it sort of under the hood. So default class operations. Managing the details of a class implementation can be tedious and error-prone. And the C++ compiler can generate a default constructor, copy constructor, so it can do all this stuff for us behind the scenes. If you provide your own implementation of any of these, you should provide your own for all of them. That's a bit extreme, I would say, but I see what they're saying. Okay, type conversion. So we've done type conversion before when we're like typecasting or doing our static cast from one data type to another. But how do we actually set this up for our own custom classes? How do we say what one class could be cast or converted to, and what happens when that conversion happens? The conversion information provided by the conversion operator is automatically used by the compiler in assignments, initialization, and parameter passing. Here's the syntax somewhat. Must be a member function of the class that we're converting from. The name of the operator is the name of the type we're converting to. The operator does not specify a return type. Here's what I'm looking for, an example. So converting a class from int val to an integer looks like this. So here's our class int val, pretty standard stuff here, until we get to operator int, open close paren, and then the implementation. Think of it this way, we're overloading the integer constructor, if you want to think of it that way. So overloading the integer constructor, which is an operator, and all it's doing is returning int val's private x data member. So automatic conversion during assignment. If we have an int val object passing in 15, we have an int I, we assign obj to I. That is doing automatic or implicit conversion when we do this. Of course, int val obj. Obj is a different type than I. Obj is an int val. I is just an int. When we do this, we're assigning an int val to an int. And when we do that, it's automatically calling this conversion operator. Let me back up one. Okay, conversion operator for the length class. So we have a length object called distance, double feet, int inches. We're setting the length on our distance. Convert and print it. So feet equals distance. I hate that they split this over 2 pages, but feet equals distance. Remember, feet is a double. Distance is some length data type. So when they overloaded that thing, they had to say what it means to convert. Basically is what we're doing here. We're assigning one data type to another, automatically converting it under the hood. The implementation of this can be found above in the kind of just the base or main text of the chapter. Convert constructors. Constructors that take a single parameter of a type other than the class in which they're defined. So here's a class that's horribly named called CC class, private data member called X, public CC class. Here's basically 1, 2, 3, 4 constructors. Here's the default constructor. Here's a normal kind of constructor that we would see. Here's a convert constructor which accepts an integer type A and a string type S. So the string class has a convert constructor that converts from a C string. So if you pass in a pointer to a char, which you kind of know is like a character array, thinking back, under the hood, C++ knows how to kind of move back and forth between an array of chars, which is a little bit cumbersome and more old school, like C-style strings, converting between an array of chars to a C++ string. So they're automatically invoked by the compiler to create an object from the past values of parameter. So if we create a new string object called S, passing in a sequence of characters, we're converting a C string. When we pass in the literal 24 to our obj constructor, we're converting an int. The compiler allows convert constructors to be invoked with assignment-like notation, such as this and this. Uses. So they allow functions to take the class type as a parameter to take parameters of other types. Basically what we just said in the previous slide. Shifting gears a little bit as we move right along through chapter 11. So aggregation and composition. These are generic object-oriented programming topics that exist outside of even really any programming language. Any object-oriented programming language will support these ideas. Class aggregation. An object of one class owns an object of another class. Composition is a form of aggregation, and when we talk about these two terms, really this composition is the more common and frequently used term. But it is a form of aggregation where the owning class controls the lifetime of the object of the owned class. Supports the modeling. If you remember nothing else from this slide, just remember this. It's a has-a relationship between classes. The owning class has a or an instance of the owned class. Easy example of this. If you're a gamer, you might have a player class. You might also have an inventory class. So the player in its class declaration would have some public or private data member that's of type inventory. So the player has a or has an inventory. This is the has a relationship. Player has an inventory. Player has a weapon. We're composing objects. The player object is composed of a weapon object or an inventory object. Here's what it might look like, another probably more straightforward example. So say we have a student info class. The student info class just has a bunch of private stuff, first name, last name, strings, address, city, state, zip. The student class, though, has as a private data member a student info object. So this student class contains a student info object. Nothing wrong with that. We haven't really seen that yet. Really, all of our classes have just contained pretty much just like straightforward basic data types, strings, doubles, chars, ints, pointers to the above. But you can put more complex objects into your class definitions. So initialization lists are used in constructors for classes involved in aggregation. They allow the constructor for owning class to pass arguments to the constructor of the owned class. What that means is you can sort of chain these constructors, if you want to think of it that way. So if we create a new student object, we also kind of need to create a new student info object. So what this is saying is we can kind of pass data down through that new object creation chain. So when I pass in parameters, we're assuming that the student owns, so to speak, a student info object. So I can go ahead and pass data down to the constructor of the student info, like this. Here's my class student. It has a private student info object. But in my constructor, what I'm doing here is I'm accepting a string for fname and lname. And here's this, it's split up onto two lines, but here's the syntax. They did put it on one line here. So this would be like your owner class student. Our owned object would be student info, but student takes in a bunch of parameters and then passes them down through this colon notation to the, I kind of think of it as like a child class. It's not a child class, that's used in a different way in this chapter even. But the owned object accepts those parameters and then does with it what it needs to. So here's the student constructor is taking in those parameters. Here's our little colon. Then it's taking that data, fname and lname, and passing it down into the personal data constructor. Digest on that a little bit. Okay, aggregation through pointers. So a has a relationship, player has an inventory, for example, just think of that, can be implemented by an owning a pointer to an object. Can be used when multiple objects of a class may have the same attribute for a member, like a student who may have the same city, students who might have the same city, state, and zip code. Using pointers minimizes data duplication and saves space. So what that's kind of saying, maybe this isn't a great example, but say we have like a student, we have a bunch of students and we have like a state class. Some class called state that represents a state. Maybe it has the state's abbreviation, the state's full name. Maybe it has like, I don't know, a bio of the state, a bunch of text that describes the history of the state. And our students, like obviously there may be multiple students from the state of Iowa. So what this slide is saying is instead of copying the full state, all the values of the state of Iowa into that student object, just take your student and point to the state of Iowa. Don't copy all that data over to the student, just point at it. Minimizes data duplication, saves space, just like when we pass pointers to functions versus passing copies of parameters to functions. Same idea of saving space and time. So lifetime. So aggregation represents the owner-owned relationship between objects. Composition, as we said, is a form of aggregation in which the lifetime of the object, the owned object, is the same as that of the owner object. The owned object is generally created as part of the owning object's constructor and destroyed as part of the owning object's destructor. So in our student class, we're obviously creating a new student info object inside of it. Because we're creating it, we got to destroy it too. When we destroy our student object, we also better destroy the student info object inside of it. 784. Let's give this one a try. Looks like a fresh example. It's not relying on too much other code defined elsewhere. 11-18. All in a single file, if I'm not mistaken. We've got 3 classes, just taking a high-level survey of the code here. Yep, 3 classes and 1 main function. All right, let's create a class called date. In it, we're going to have a private string called month. Yeah, that's fine. We're going to have a string called month, an int day and year, int person ID. What is that? Comment ID of person whose B-day this is. Okay, random. Public section. Here's a constructor. String M, int D, int Y. Oops. Yeah, then int ID. Okay, so we've got our 4 parameters there. Then we're going to sort of chain or pipe this down into, let me make sure. Yeah, okay. Month, day, year. Good. Okay, we're going to pipe this down into our month constructor, which is a string. So if you actually hover over the month text here, you get a little pop-up saying it's a string. So we're like passing this M down into the string constructor. We're passing in D down to the day constructor, passing Y into the years constructor, which is an int. And then person ID gets ID. Boom. So yeah. DOB object for person ID has been created. Destructor for date. DOB for object for person. All right, here's one class, here's another class. Not too much new going on there other than this special syntax where we're passing data down to the constructors of these respective data types. Do you have to do this way? No, it's like just flexing on the new syntax that we learned. So bear with it. I would never want to see this in like any real code. Again, this is just a demonstration of the syntax. I suspect down here in the person class, sorry, the country class and the person class, I guess, we're going to see examples of where that would actually be useful. Let's create class country, class person. So in country, we're going to have a string called name, public section. Here's our constructor country, string name, passing down to the string constructor cout. A country has been created. Destruct deleted. We deleted a country. All right, person, string, name, date. Here we go. Here's some composition. Date of birth. Int, person ID. Shared PTR. A little syntax from a previous chapter. Country, so a country pointer. Good. Public. I'll mention why we're using a shared PTR there in a second. Person constructor is going to accept a string called name. String for the month. Int day, int year. Shared PTR. Type country. Reference. Called PC, pointer to a country. And then some more funky syntax. I got a colon right there. And I'm going to call my other constructors name, date of births constructor. We're going to pass down month, day, year, person, colon. What? Did we miss something? Unique person ID. Person ID. I'm not sure what that is. Person. Maybe it's down below. This is the trouble with splitting this code over several files. Yep, right here. It's a static. Way at the bottom, bear with me here. At the bottom of this person object, we have a static int unique person ID, which is used to generate PIDs, or at least simulate it. Let's grab this destructor as long as we're here, so we don't forget it. Cout person object has been destroyed. Okay, cool. So here we got our static. We can go back over here. Make sure we're... So we got our date of birth constructor, month, day, year. Okay. Grab our person, pass down the static unique person ID. Good. Chaining more together. So person ID, person, colon, unique person ID, comma, P country, passing in that PC pointer. Yuck. Don't like that. Okay, so we got all this constructor done. What are we actually doing? Okay, cout person object, person ID has been created. How exciting. We're going to say person, colon, unique person ID plus plus. So with every new person that gets created, that unique person ID is going to be incremented by 1. In this way, we'll be able to see how many total person IDs or people have been created. And I think what you'd want to do too, if you truly wanted to see like how many people existed in your program, when you destroy a person, I would say also decrement unique person ID here. So this is really just going to be accurate to tell us how many times we've created a new person. Doesn't tell us how many people are necessarily still in scope in the program. To do that, you'd want to decrement unique person ID in the destructor of the person object. All right, that's all the new object stuff. Outside of main though, we are going to take int person, : unique person ID, assign it equal to 1. And I haven't forgotten about the shared PTR up here for P country. We're about to explain what that is. Shared PTR country P USA equals make shared country passing in a string USA. Okay, keep that in the back of your mind. Create a person object, so shared PTR person P equals make shared person pointer. All right, Peter Lee, January 1, 1985, P USA. So there we go. We saw the P USA, that shared pointer. And what I think I'm going to do, create another person, P1. Yeah, let's do a copy paste job. This is a lot of syntax. I'll just make this P2. Be consistent. P1. All right, so we're creating another person. Let's just change some data. And PUSA. Now there are two people. So both people will go out of scope when main returns. What is with the shared pointer for country here? Well, if you think about it, both people share this pointer. So that's going to help us keep track if one person is destroyed. That will help PUSA basically stay in memory and not get destroyed either. Cool. I think this is the last big idea, of this chapter. Inheritance. Big idea in this chapter, big idea in C++, and a huge idea in all of object-oriented programming. So what is inheritance? It's a way of creating a new class by starting with an existing class and adding new members. The new class can replace or extend the functionality in the existing class. Inheritance models the is-a relationship between classes. Think about this. A player has an inventory, but a dog is an animal. You hear this a lot. You hear this is a versus has a relationship. Has a is your composition. It's that idea of composing two objects together. Is a is more of a hierarchical inheritance kind of tree top-down approach, however you want to think about it. Inheritance is a, composition is has a. So a dog is an animal. An animal is a living being. All kinds of examples of this. Some terms. So the existing class is called the base class. Alternative names for this are parent class or superclass. The new class is the derived class, also known as child or subclass. So if you had an animal class, that would be the base class or the superclass. The dog class that inherits from animal would be the derived class or the child class or subclass. I honestly use all these terms. Here's the syntax. So we have an existing class called base. We have a derived class or a child class that extends. Whenever you see the colon used in this way, you can think extends. Derived extends public base class. And what that means is now that everything that the base class has, the derived class now has access to it. I wouldn't say everything, most stuff. We'll talk more about that in a minute. It is definitely not everything though. It could be, but not by default. Inheritance of members. So class parent So who gets what, basically? So if we have a parent class, we have an int a and a void bf. We have a child of the parent. Class child extends the parent class. It has an int c and a void df. So the objects of parent have this int a thing, and they can access the bf method. The children have an int a from the parent, void bf from the parent, int c from the child, df from the child. Take a peek at a hands-on here. 791. We'll just take a look at it. Just a read only. Okay, so this is including some class called inheritance.h, and I think we need to back up a little bit to see what all that is. So we have a class called person. We have some enums here. Good little review of enums. So we have an enum for discipline and an enum for classification. Remember, we have a class called person. Then we have a class called student, and a student is a person. Remember, student is a person. So everything that person has, student also has, as long as it's in scope. We can take that one step further and say, okay, faculty is a person. So we're getting like more and more specific in our objects that we're creating. The very generic person is at the top of the stack. The student is in the middle. Sorry, the student is not in the middle. Student extends person. Faculty also extends person. So if you're thinking about this in terms of like a hierarchy, student and faculty are in the same hierarchy in this inheritance chain. They're both children of person. Student has different stuff than a faculty, but everything a person has, the student and the faculty also have, as long as they're in scope. I always have to add that caveat. And I would recommend you go through, in the interest of time, I'm trying to keep this a little shorter, go through 1119 and try this out for yourself. So in dealing with inheritance, objects should be created using dynamic memory and accessed via pointers that allocates to memory. So a method that expects an argument of the base class may not have the space needed to accept an argument of the derived class, even though the object is a object of the base class. Use pointers to initialize pointers to objects instead of objects for parameters, lists, and arguments. So use pointers instead of objects. All right, back. Sorry about that awkward jump. Protected members and class access. If you remember back when we talked about like public and private, in our introduction to object-oriented programming, we said there are a couple ways to control who can access what in a given class. Private means only that class can access that class's stuff, whatever is defined as private. Public means that anybody can access it, but there is a third option here. There is protected member access and specification. So if your class is labeled protected, a class member labeled protected, you can access member functions of derived classes as well to member functions of the same class. Similar to private, except accessible to member functions of derived. So if we look back, we could add a protected section to the parent class, and the child could then access all the protected stuff of the parent. If parent had private stuff, the child wouldn't even be able to access the parent's private stuff, even though it is a child of the parent, because the parent's stuff is private. The child could not access it. If it's protected, then the child could access it because it is a child of that superclass. Base class access specification determines how private, protected, and public members of the base class can be accessed by derived classes. All right, 1122. Looks like there's no external code dependencies here, so we can take a look at this top to bottom. All right, we've got a class called person. We have a couple enums up here too, but a class called person. It's got a protected section. It's got a public section. Then we have a class called student, which extends person. So a student is a subclass of person. It has a private section, a major, and a shared pointer to an advisor. It's got a bunch of public stuff too, similar to what we've seen before. We've got a faculty as well. We've got a public class T-faculty, which extends faculty. So this is like taking the inheritance one step farther. So we've got at the top of the list, we've got a person, then we have a faculty, then we have a T-faculty, which extends faculty. Going down the rabbit hole here. And you can imagine, like in a very complex programming project, very complex application, these hierarchies can get absolutely insane. They can go, in some cases, tens of levels deep, like 10 to 20 levels deep. If you're taking my Unreal Engine class next semester, Game Development 2, you will see firsthand how deep these hierarchies can go in terms of like a real-life industry standard game engine. So these hierarchies are real. They can be complex. You just have to keep in mind what is a parent of what. Let me back up one. I wanted to point out that protected section. Protected person. So any child of person can access this protected name. So we can do stuff like this. When we construct a student, we can pass in name, and that'll get handed down to the person constructor. Base class access. So C++ supports 3 inheritance modes called base class access modes. Looks like this. So public inheritance, protected inheritance, and private inheritance. This was actually somewhat of a new topic for me. When I was learning C++ below these many years ago, this wasn't really a thing. At least I didn't know about it. But you can also support inheritance modes. So you can say parent, child extends parent. So parent is the parent of child, but it is a public parent, or it is a protected parent, or a private parent. So the base class access is not the same as member access specification. The base class determines access for inherited members, but the member access specification determines access for members defined in the class. So specified using these keywords: private, protected, public, like we've seen before. So here's the new one, I guess. This sounds like a very fun function. Base class and member access specification. So we have here the base access, we have member access, member access. So when you see access set in this way, this is like setting the access level at a higher level than setting them for individual members. It's like a different, how should I say it? It's like an umbrella way of adding access to a class. You can do it at the top level like this, but you can also do it at the member level like this on a one-off or individual basis. Okay, these mostly a review here. Public objects of derived class can be treated as objects of the base class, not vice versa though. Protected is more restrictive, but allows derived classes to know some of the details about the parents, and the private access specifier prevents objects of derived classes from being treated as objects of the base class. Here's a nice little chart that illustrates that. So if your base class members, public X, protected Y, public Z, if you have a private base class, here's how those members appear in the derived class or the child class. So if X is private, X is inaccessible, but because we have a private base class, now Y is also private. It sort of overrides that and says now in the child class, Y is private. Because of this private base class, even though Z is public in the parent class, when we say private base class, Z is now private too. Talking about protected base class. So in our parent class, X is private. In our child, X is inaccessible. So it's still basically private. You still can't get at it. In the protected Y, we still have a protected Y because the base class is protected. We have a public Z, but now Z becomes protected. Let's see what public does. If you have a private X, X is still inaccessible. You have protected Y, it's still protected Y, but public Z is still public Z. So take a look at this and see if you can see the pattern. It's like if something in the parent class is private, we're still respecting the fact that it's private in the child. It's like we're not overriding access specifiers that are more restrictive. I guess you could say it that way. Protected, let's do this one. Protected is more restrictive than public. So when we say the base class is public, we're not going to be able to override that protected. Up here, when we said it's protected, we're not overriding the private, but because public is less restrictive than protected, we can override that and say that it's protected Z. Yes, this sounds confusing. I've made it my whole programming life without needing to use this, and I suspect you will be able to do so as well. But if for whatever reason you need these broad brush strokes when defining access modifiers, you can use this method. Constructors, destructors, and inheritance. So by inheriting every member of the base class, a derived class may contain a base class object. Derived class constructor specifies which base class constructor should be used to initialize the base object. Oops. Yes. When an object of a derived class is created, the base class's constructor is executed first, followed by the derived class. So base class constructor first, then derived. When an object of a derived class is destroyed, its destructor is called first, then the base. Think about it, it makes sense. If I destroy a child object, the child object is destroyed first, then the parent is destroyed. If I destroy a player object, the inventory object would need to be destroyed first, and then the player object. That's more of a has-a relationship, but in the dog example, if I destroyed my dog object, the dog object gets destroyed first, then the animal object above it gets destroyed second. Order of execution. So if a student is the base class, undergrad is derived. They both have constructors, destructors, and an int main. When we create an undergrad object called U1, we execute the student constructor, then the undergrad constructor. So the base class or the parent class gets executed first, then the undergrad constructor gets executed. When we return, the undergrad destructor runs, then the student destructor runs. Passing arguments to a base class constructor allows selection between multiple base class constructors. You can specify arguments to a base class constructor on the derived constructor heading. Can also be done with inline constructors. Must be done if the base class has no default constructor. Here's an example. Here's our parent class. Here's our parent constructor, 2 ints. Here's our child, which extends our parent class. It has an int z and a public section, which calls, well, here's our child constructor. It's going to call the parent's constructor and then do some stuff. So the child, when you create a new child, you accept an int a, and you pass that int a to the parent constructor. Parent is created first, then the child is created. Overriding base class functions, and we're almost done, just shy of 2 hours. Overriding a function in a derived class that has the same name and parameter list as a function in the base class, used to replace a function in the base class with different actions. Not the same as overloading. With overloading, the parameter list must be different. So this is like saying, if I have a parent class that has like a print method, I print, let's use an animal base class, an animal parent class. Say I have a print method in the animal class that prints out generic information about the animal. If I override that base class function in my dog class, if I have a print method in my dog class, that overrides the animals print method and will print dog specific stuff. Access to the overridden function. When a function is overridden, all objects of the derived class use the overriding function. If it is necessary to access the overridden version, it can be done using the scope resolution operator with the name of the base class and the name of the function. So you can still get at it. You can still get at the parent function that was overridden. All you do is specify the base class name, : function name. Okay, one thing I wanted to check for, it's not in the PowerPoint. C++ is kind of weird if you haven't noticed already. Here's a nice diagram. An insect is the base class. Bumblebee is the child, or grasshopper is the child of an insect. They may not even mention it in this book because it's such a bad idea, but C++ is full of bad ideas. Why would we stop now? I don't even know if it mentions it. I thought it did in the... It does not. C++ is one of these few languages that actually allows multiple inheritance. Multiple inheritance is bad, don't use it. But what that means is, I'm getting back to my insect picture. What that means is if you have a bumblebee or a grasshopper, so these two both inherit from insect, but multiple inheritance means that it could also inherit from something else. Like, I don't know, flying animal or something over here. Bad idea, gets confusing very quickly, don't do it. Your classes should only inherit from one parent class. Again, C++ is the only language that I know that allows this. You can sort of do this in a much better, cleaner way in other languages. It's not called multiple inheritance. It's called this idea of interfaces. It's like I say, it's a much better, cleaner, more sort of pure way of getting multiple inheritance. But C++ just allows you to extend from A to B and everywhere in between. That didn't make sense. It's been a long lecture. I think that's good enough for now. This has been Chapter 11. More on object-oriented programming and classes. The assignment has been published. It will be soon if it hasn't already. We'll see you back here next time for Chapter 12. Thanks so much.